All right, so perhaps I should start teaching this in Algebra 2, which I think I probably will. So one of the things that we do teach in Algebra 1 and Algebra 2 is a difference of squares. Like if you had x squared minus 25, that factors into x plus 5, x minus 5. But there actually is also, you can do a sum or difference of cubes. And so to factor a sum or difference of cubes, I'm just going to give kind of the general rule. Let's do a difference first. If you have something that's perfect cubes, a cubed minus b cubed, there's an outside factor, and that outside factor is just, you're going to take the cube root of those things. And so it's just a minus b. And then the second is a quadratic factor, and the quadratic is going to always be this one squared. You're going to take the product of this, AB, and you make it positive. And then this would be B squared. And you cannot factor any further than that. So you're not going to be able to take this further. Okay. So just realizing that the A and B are coming from these, what the cube root of those are. So they're going to have to be perfect cubes. We'll do an example in a second. Like maybe it would be x cubed minus 8. What's the cube root of 8? 2. Or maybe it would be like x cubed minus 27. What's the cube root of 27? 3. Okay, so it would have to be things that are perfect cubes. All right, let's do the sum. The sum, what happens is it's the same factoring except these signs are switched around, okay? So this time the outside factor is a plus b, and the inside, or the quadratic, is a squared minus ab plus b squared. Okay, so let me show you why that works, because you might not believe me. What's the reverse of factoring? Multiplying. So if I were to multiply these two together, they should equal that, correct? Okay, so let me show you that in fact that's the case. I'll just show it on the board a second. So let's take, what I'm trying to prove is if I did this times this, that I would get that. All right, so what's a times a squared? A cubed. This would be plus a squared b plus ab squared. Okay, now I'm going to do everything by this. That sign, because it's a negative, that would be minus a squared b minus ab squared minus b cubed. Okay, I know there's a lot of a's and b's in different exponents. This is an a squared b. Do you see how that's minus an a squared b? Those cancel. This is an ab squared minus ab squared. Those cancel. You're left with a cube minus b cubed. So that's why it works, okay? So now let's try it. All right. Can you factor x cubed minus 27? Okay, so here's how this works. The a and b are coming from these terms, and I got to figure out what, these are cubed, right? So obviously this one, the cube root of x cubed is just x. And what's the cube root of 27? 3. So this is like the same thing as x cubed minus 3 cubed. So my a and b are x and 3. All right, so the first factor would just be, what do you think? X minus 3, good. And then this would be x squared. What you're going to do to get this is you're literally going to just take those two and put them together. X times 3 would be plus 3x. And then plus 3 squared, or 9. That's how you factor that. Okay. How are we doing? All right, so this is what I'm going to have you try now in your notes. Would you find the limit as x goes to 2 of x cubed minus 8 over x minus 2? What's the problem? Try the cheat. So what's the problem with the cheat? 0 on the bottom. Okay, so this is why I did this. Can you try factoring the top and seeing if you can get it to cancel? Try it in a minute. Helps, right? Your difference of cubes, this is like x cubed minus 2 cubed. So your outside factor here is x minus 2. Inside, did you have x squared plus 2x plus 4? Good. What that allows us to do then is it cancels out our x minus 2's. And then it would allow me to put in my 2 to this function. So that would give me 2 squared plus 2 times 2 plus 4, which is 4 plus 4 plus 4. So a limit of 12. How did we do? Do you have any questions for me on that? Okay. Then what I decided to give us for squeeze theorem is a handout. We're not going to do all of these, but this is from the flipped classroom. I use their resources a lot. They have a ton of stuff for calc. And so there's like a little note page and then some practice. We're going to do some of these together today. Okay, the squeeze theorem or sandwich theorem, our book calls it the sandwich theorem. Other books call it the squeeze theorem. The idea is this, okay? Let's say you know you have some limit And you try factoring, you try all kinds of, you can't remove the 0 on the bottom, okay? But what I tell you is this. So here's my function in the middle, we'll call it, so here's like my function in the middle. And I know that there's two functions that f of x always stays between. So I tell you, hey, it's always going to be less than h of x. Okay, so I have this function h of x here. It's always going to be less than h of x. And it's always going to be greater than, well, I flipped it around, but that's okay, g of x. Okay. So the concept here is that, do you see how h and g like are kind of squeezing that function f together? So if I know h of x limit and I know g of x limit, would you agree, even though I don't know f of x's limit, that it's going to stay between those two numbers? So that just kind of logically makes sense to you. Okay, that's really all the squeeze theorem is it allows us potentially to evaluate limits of something that we know stays between two other functions because we know it stays above a certain value and below. And what's even more interesting is if those limits go to the same thing. Okay, so we're going to fill some things in here. So we're going to call this function if h of x is less than or equal to f of x, and that's less than or equal to g of x. It's kind of like what I have going on here, except I flipped them around. And let's say I told you the limit as x goes to some value. So the limit as x goes to c, let's stick a c there. C is just a random x value. Of the function g of x is, we'll call it L. L for limit. And then I also tell you that the limit of h of x as x goes to that same x value, c, is also L. What that tells us is since f of x is squeezed or sandwiched between g of x and h of x, even if I don't know what the limit of it is, I really do. Because at that point, the limit of f of x as x goes to c is also going to be L. Okay. So here's a really good example of this. And last year we called this, I don't know if you remember this, damped oscillation. Do you remember that phrase? Do you remember how it oscillated between two curves? That's kind of what a good visual of what the sandwich theorem is. The inside thing is going to be something we can't evaluate. So let's do this one right here. If I asked you, hey, can you evaluate the limit of that? What's the problem with that? What's the issue there? And it's not something I'm going to be able to remove. Agreed? Okay. So, but what I will tell you is what we learned last year is this is going to oscillate between x squared and negative x squared. I'm going to grab my graphing calculator and show you that in a minute. Okay. So out in front I have x squared. And then, what does x squared look like? Just draw it in the air for me. Parabola. Negative x squared, right? Okay. So, then there's that. Let's see what happens. Uh-oh. I had to reset this, and I wonder if I'm in degree now. No, I am not. Okay. Let's do zoom 6 again. Okay. I'm going to also put down here, so we have x squared negative x squared. Okay. So I don't know if you see that blue curve, if I zoomed in a lot, so zoom in. Okay, do you see the oscillation going on in there? That's that curve. Okay. Do you see how the red and the black squeeze the blue? Is that making sense to you? Okay. So what I would say then for this is that I know that this is going to be squeezed between 0 and 0. How do I know that? What was this function? X squared. You guys told me you saw that it was squeezed between x squared and negative x squared. Agreed? Can you evaluate x squared when x goes to 0? Can you evaluate that when x squared goes to 0? Use direct substitution. What's that limit when x goes to 0? Just 0. Okay, that's how I got these two things. So if I know that, then I know that the limit of this whole thing is also going to go to 0. Okay, let's try another one. Let g and h be the functions defined by negative x squared plus 2x minus 3, and h of x equals 2x plus 1. If f is a function that satisfies this, g of x is less than or equal to f of x is less than or equal to h of x, what's the limit of f of x as x goes to 2? Okay, so what I'm saying is, in order for this to work, if I know that f of x is between g of x and h of x, I'm going to find both of their limits. And if both of them go to the same value and I know f is squeezed between them without knowing f, I'm going to be able to figure out its limit. Okay, so in your groups, would you please, given that g is this function and h is this function, would you please find their limits as x goes to 2? Did you guys come to a consensus over there? Would you check a minute with each other? You get the same thing? Yeah? Okay, what'd you get for g of x? 5? Uh-oh. That's what I got. G of x. Negative x squared means, don't forget your order of operations, you got to square it first. 2 squared is 4, so that would be negative 4. Plus 2 times 2 is plus 4 minus 3. Okay. Negative 3? That's, okay. Paul, what'd you guys get over here for h of x?
5.
This one was 5. Okay, so then, can I find the limit of f of x exactly? Yeah, but I don't know what it is. I know it's between those things. So what I would say is the limit of x over 2 of f of x can't be determined by squeeze theorem. Okay, so I just have given you two examples, one of which you could determine, the other of which you can't determine. And so that's kind of how you check for squeeze down. All right. What I want you to do is we're going to just do some practice together, because so you can have that